Hello, everybody. It's my pleasure to welcome you all for this second general seminar of IPhT. So the speaker today is David Andelman from Tel Aviv University. So David is a friend of mine, a colleague, since we know each other more than 40 years from MIT. And so David did his PhD at MIT, then he went for a postdoc to Collège de France with Pierre-Gilles de Gennes, then to Exxon, and then went to Tel Aviv University, where he has been since 87, I think, or something like that. So David has had many prizes and distinctions. He's a fellow of the APS. He had a Humboldt Prize. And he was also a member of the visiting committee of CEA, of the whole CEA, twice. And also, what else? A member of the jury of advanced ERC grants. And so today, David will talk about 100 years of electrified interfaces. And so please let us know all about it.
Thank you. Thank you for coming. Thank you for inviting me. So before I start with the talk, I want to pick up on what Henri told, that we know each other for 40 years, over 40 years. And actually, you know, I was looking through my files and I found this copybook from MIT. I'm not sure if you can see what is written here, but I wrote the same here. So this is my copybook from spring '82. Henri was a visiting professor at MIT, and he gave a course on disorder systems, including explaining us about the great Parisi work that led him later last year to a Nobel Prize. And from that time, we became very good friends. We collaborated over the years, you know, dozens of papers together. Henri worked with almost all my students, and it was a really great friendship, and I'm very happy that I can talk here in this environment where is the home base of Henri. Well, yes, I had another nice picture with you with this cowboy head, but I thought that maybe they will not recognize you. So, I mean, most of the people here are young. Yeah, this is how Henri looked about 10 years ago, I think, when we celebrated his 60th. Okay, so this was one small story. Let me now start my talk, but I will start it with another short story. And the story is not about 40 years ago, it's about 100 years ago, which is relating to the title of my talk. So in 1925, Peter Debye was already a very well-known established physicist, and at the time he was working at ETH in Zurich. And one day, a visitor was announced, and he came to his office, to the office of the respected professor. It was a tall, slim guy, and he came to the office, and without any introduction of himself or any small talk, he just came to him and he told him, Professor Debye, your theory on electrolyte is wrong, is incorrect. And Professor Debye asked this guy to sit down, to relax, and to explain him what's going on, why is it wrong. And not only that he was convinced that this young person, he was maybe 20-something, is right, and his theory was wrong, but he also offered him an assistantship the next year. And you can guess, of course, the name of this young person was Larson Sager. So this is how Larson Sager looked. I think is when he was 18 or something like this. And 43 years later, after this encounter with Peter Debye, Larson Sager got the Nobel Prize in '68. And he was awarded the Nobel Prize for his discovery of what is now known as the Onsager relations, the reciprocal Onsager relations, which are fundamental for the thermodynamics of irreversible processes, which is very much in fashion today. Many people work on out of equilibrium thermodynamics, active matter, and so on. Now, Onsager, probably he was one of the greatest physicists of the 20th century. Probably, in my opinion, I think in many others, he was the most renowned statistical physicist of the 20th century after the big names, Gibbs and Maxwell and Boltzmann of the 19th century. And so I told you about the work that he did that awarded him the Nobel Prize. This is work that he did in the 30s, 19 years ago. But he also did two other works that were really revolutionary works, and I'm sure that many of you know them. One is that he solved the two-dimensional Ising model exactly. This he did in the late 40s. And this by itself was a revolution because it was the first time that critical phenomena could have been established on a rigorous basis and not with some approximation. The other great thing that he did more or less at the same time, he has proven that for long molecules, you have a real transition as function of their concentration from an isotropic phase to an nematic phase. A nematic phase is a phase of liquid crystal where you have a spontaneous breaking of the ordering parameter, which is the orientation of the molecule. It's a big molecule, so the orientation goes with the elongated molecule. Now, I'm not going to talk about any of these three great works that he did. I'm going to talk about what is closer to my heart, but it's work that Onsager did throughout his career. If you look on his works, he started with the work that actually is related to the work of Debye and Haeckel on electrolyte. And throughout his career, even in the 60s, before he died, he continued to work. He had dozens of papers on electrolytes. And this is what I'm going to talk about. So he had many works on electrolyte, but he touched many, many topics, turbulence, dielectrics, helium-2. All of his work, about 95, it's not such a huge number, are collected in a very nice volume. You can buy it if you want. And the volume also includes this article by Michael Fisher and others, where the story that I told you is mentioned there, along with his many biographical notes. Of course, he was an extremely eccentric person. His teaching was catastrophe, even was fired from a university in the US, from Brown University, because nobody understood his lecturing. But then at Yale University, people understood that this is not a regular person, and they gave him, although he was teaching a course in statistical mechanics for graduate students, and the student called it Introduction to Norwegian Mechanics or whatever. But in any case, eccentric person, but extraordinary. Okay, so this is the outline of my talk. I'm going to cover very briefly 4 different topics. I will start by giving an introduction to the 100 years Poisson-Boltzmann theory, and then I will talk about 3 different things where you see the name of Onsager enters in all of them. There are different properties of electrolytes, of ionic in liquid solution, the dielectric properties, surface tension, and conductivity. He worked on all of them, and in recent years, we improved on his works. But he did the seminal work. Okay, so let me first start with some introduction about why at all look at ions in liquids. And the reason is that on Earth, the most abundant solvent, of course, is water. Water is sometimes called the universal solvent. You can solubilize many, many things in water, not everything, of course, but polar molecules, ion molecules that dissociate, like salt, and many things. And our body, the biological system, our body, is actually majority of our body is water, and all the processes in the body are, all the biochemical reaction are made in water environment. So you have, in our body, you have simple ions like NaCl inside the cell, in the blood, and so on. This is a cartoon of a biological cell membrane. The cell membrane is built from lipids. Many of those lipids are charged or polar. This is another cartoon of DNA. As you know, DNA is highly charged polymer, highly charged macromolecule, and you have other types of RNA or proteins and many other things that are also charged in water. So in terms of the biophysics, it's very important to understand electrostatics in the environment of water. The other thing is that many of the compounds that we use on the daily basis, soap, shampoos, paints, milk, they are all paints that are water-based paint. They are all in water, and many of them have charges. The macro bodies are charged, and there are counter charges in the solution, in the aqueous solution. So this is, again, another area where electrostatics is extremely important in liquids. In terms of the statistical mechanics, the more fundamental problem, you have to solve the statistical mechanics of Coulombic systems that have Coulomb interaction, 1 over r, very long-range interaction. And this is, again, a cartoon where you see this is the water. The solvent is water. Of course, water is not a continuum solvent. It's made of molecules, and I will go into that a little more later. So you have a dielectric solvent. You have some macro ions in the solution where you have some charge distribution of those macro ions. Yeah, these are the macro ions. And you have small ions that are floating in the solution. And everything is dynamic. Everything is rearranging. Even in thermal equilibrium, everything is, of course, rearranging. You have fluctuation. And you have to solve all this while you have to take into account the fact that entropy is more or less the same order per degree of freedom, is the same order of magnitude as the electrostatic interaction. So you cannot ignore entropy, and you cannot ignore the electrostatic interaction. You have screening and so on. The solution, the exact solution of this problem is not possible to do in an exact form, but of course there are many approximations. And one of the most common approximation is what is called the Poisson-Boltzmann theory. It's sort of a benchmark. So if you do some better, you always will compare with the Poisson-Boltzmann because it's very simple and it can be solved numerically or analytically. So just a word about the Poisson-Boltzmann theory. So of course, Poisson, the very productive French scientist, and Boltzmann, the Austrian physicist, they didn't share any year that they lived together. Boltzmann was born 4 years after Poisson died. You can see from my transparency. So there's no way that it's not a collaboration between Henri and myself. So maybe in the other world, but it's just a name that we give because it's using the Poisson equation of electrostatic together with a Boltzmann distribution. So it's very simple to show. So Boltzmann distribution, we take the Boltzmann distribution for ions, and we just take psi, which is the electrostatic potential. We don't take any other type of interaction. And this is the local distribution that depend on the local potential, which of course depend on all the other ions that are around. And Poisson equation is always valid. So Laplacian of psi equal to the local charge densities. I take here for simplicity a monovalent ion, plus and minus 1 valency. And if I plug in the first equation into the second one, I'll get the Poisson-Boltzmann equation for this simple case. Of course, I can write it for more complex cases. And this is a nonlinear equation, second order, partial differential equation. I know the boundary condition. In principle, I can solve it either analytically, approximately, or numerically. And One thing to remember, though, is that when I wrote these two equations, especially the Boltzmann distribution, I already made a big approximation. I made the approximation, which is more or less a mean field approximation. I made the approximation that any ion just sees the mean field of all the other ions dictated by psi, and it doesn't see every position of the other ions. And also that there are no other interaction non-electrostatic besides psi. Now, boundary conditions, the simplest one, as we teach and we know from freshman physics, is a constant potential on the boundary or constant charge. On the boundary is the Dirichlet, the Neumann boundary condition, but there are also other more sophisticated and more relevant to physical and biological system, and this is called charge regulating boundary condition. I'm not going to talk about it, but it's a boundary condition which self-adjusts with other degrees of freedom. Okay, so once you know in principle that in order to solve the Poisson-Boltzmann, if you know what are the ions, what are the macromolecule, what are the charge density, what are the electric constant, you can either go and find some solver on the net. One of the one that is quite available, a freeware, it's what is called Poisson-Boltzmann organization, you see org, funded by the NIH. You can, if you are a biologist, you just plug in the charges, the partial charges, you plug in all the parameters, and the solver solves the Poisson-Boltzmann and give you, for example, the interaction between a protein and a cell membrane. Some ligand that comes and want to, a virus that comes and wants to enter into the cell, there is electrostatic interaction, and you do that. And also I mentioned here that Henry with his collaborator also have also another solver, and there are many others. But if you want to look a little bit more into the fundamental of what are the important length scale, the energy scale, and this is what I'm going to do, I would like to introduce some of the important concept of the problem, and to do that, I have to start with a very, very simple system. Let's imagine the system that was considered by GUI. Of course, you know that GUI was a famous French scientist. I learned from Bernard Duplantier from his nice article about the Brownian motion that GUI was very much involved in the Brownian motion before Einstein. I think also there was some correspondence with them. Nevertheless, he was very active in the late 19th century, and in 1910, before the First World War, he wrote this article where basically you take a charged surface with some continuum charge density, sigma, and you put it inside a bath, where in the bath there are only the counter ions. So the total amount of counter ion balance the charge on the surface. And you solve this problem. It's a nonlinear Poisson-Boltzmann equation, one dimension, ordinary differential equation, you can solve it. And the solution is this, what I showed here is this logarithmic solution. The potential depends logarithmically on the distance from the wall, and there is a characteristic length that we call it after GUI and Chapman. I didn't mention, but Chapman was an Englishman who solved in parallel the same problem. You know, the fact that there is 3 years different doesn't mean that he copied from him, because at that time, the GUI published in the French journal and Chapman in the English one, and there was no communication. So in any case, you can see that this is the GUI-Chapman length. It's important to see that it depends both on the temperature, because you have entropy that doesn't want the ion to condense on the surface, because if you condense all the ion in a layer, you are going to lose the entropy if you can disperse them. But there is also the attraction of the surface to the ion, so it's a competition between the two. And you see that both enter, the entropy enter versus the thermal energy, and sigma enter here. So this length goes as proportional to 1 of the surface charge density. And if the potential is logarithmic with this factor 2, this means that the density of the counter ion will go as this algebraic form also with this L star, and far away it will go like 1 over z squared. So it's a long decaying counter ion density profile, and it's very reminiscent of a critical phenomena where the correlation function decay algebraically at the critical point and not exponentially. So this case where you don't have salt, you don't have also the negative and the positive ion, you just have the counter ion, is the strongest electrostatic case. And it's in this sense, it's close to the critical phenomena. So you can see that the profile is diffusive because it has such a long range. 10 years later came the work of Debye and Haeckel. This is not the work that Onsager commented on, but they had a series of work. This is a work from 23. And in this extremely seminal work, nowadays we look and we say, of course, it's so trivial and simple, but at the time it was really a breakthrough. What they understood is that if you have salt, if you have both the negative and positive, the electrostatic interaction will be screened. And it will be screened exponentially, not algebraically. And this screening is because each ion is encircled with a cloud of both positive and negative ion, and this cloud that is self-consistently for each ion will reduce the electrostatic interaction between two ions, and it will not be 1 over r, it will not be the Coulombic one, but it will be an exponentially decaying one, and there is an important length, the screening length, that is written here, and the screening length lambda d after Debye in units of molarity, and I remind you that 1 mole, a unit that I'm going to use a lot, 1 mole is 1 molar is a unit of concentration. It's 1 mole per liter. 1 mole is 1 Avogadro number per liter. And this is the number that people use in electrolyte solution studies. So you can see that the potential is exponentially screened with this lambda d. And the screening length depends on the concentration. If you put more and more salt, you have more and more screening because you have more, and the distance between ions will be smaller. So for 1 mole of salt, which is a lot, for example, in our body, if you get an infusion of physiological saline, it's about 0.1 or 0.14 molar. So this is about 10 times more. Seawater is about 0.6 molar. So this is quite concentrated. Lambda d is 3 angstrom. In pure water, just because the water itself will dissociate into an H plus and OH minus, it's much, much bigger. It's about a micron. Of course, you never have really pure water. You always have some impurity. So lambda Debye varies from few angstrom to, let's say, 1,000 angstrom. And you can see that if you solve the Poisson-Boltzmann equation in the linearized form, you get exactly the screening also for the potential of a single wall, and the potential will decay exponentially and not algebraically. Okay, the third length is something that I will use. It's less important, but it just sets the electrostatic scale. I told you that KT competes, thermal energy competes with electrostatics. So if you try to see at what length KT is exactly equal to electrostatic interaction in water with the electric constant of water, which is big, 80, you get 7 angstrom. So this length is called the Bjorn length, named after another scientist that worked 100 years ago on this system. And this length basically sets the scale. So it's very convenient, for example, to express lambda Debye with this length. You see all the prefactor going away, and you just are left with this length and square root of the concentration. Okay, so this was my little introduction. I'm going now to go quickly through 3 different problems. The first is the phenomena that is well known. The dielectric constant of seawater is much below the dielectric is much smaller than the dielectric constant of pure water because of the salt. It sounds a little bit strange, yes, because usually you put salt or you put some polar molecule, you would think that the polar molecule should make the water even more polar. But it's not like this, and there is a reason for this. But please remember that water by itself is extremely polar. It's one of the most polar liquids. There are, of course, liquids that are more polar, but it's one of the most polar liquids. Epsilon equal 80. You look on alcohol, on oil, it's about an order of magnitude less. And this phenomena of the dielectric decrement, the decrease of the dielectric constant, is related to the hydration shell of ion by water molecule. So this is the first time that I'm taking you away from Poisson-Boltzmann, because I'm saying that water is not a passive continuum media. Water is form of water molecule like this, and because of the partial charges between the oxygen and the 2 hydrogen, this delta, the charges are distributed differently. The water molecule itself has a very strong dipolar moment. Now, imagine that I have water with this strong dipolar moment, and I'm going from now on to take just a point dipole. I'm not going to take the real structure of the water molecule. It's a bit too complex to do analytically. So what is a dielectric response? The dielectric response is you put a small electric field, external field, and you see how the system reacts to the field. Any system, any material, if it's conductive or dielectric, is non-conductive, isolator, it will have a response because of the polarity of the constituent. Now imagine, so this is what I call epsilon of water, just water. This constant is equal to 80. And now imagine that I put just 1 ion in the water. If I put 1 ion here in the water, there will be a strong charge dipole interaction of the water molecule, and then you create a hydration shell. You create it's not a completely static and isolated, but it's a very well-defined structure of water, usually 1 layer of water or 2 layers of water that are pointing very much toward this central ion, because in the short range, the interaction is very strong. Now, imagine that on this system, 1 ion, hydration shell, and then all the other ions are moving. I put now an external field, and I measure the dielectric constant. It will be less, because the ions that are in the dipoles that are in the hydration shell will not be able to respond so much, because they also feel the strong electric field that comes from the ion. So this is a hand-waving argument to tell you that because of this effect, not because of the polarizability of the ion, but because of the fact that I'm localizing some of the water molecule in a layer, this is the reason why the dielectric constant in presence of some concentration of water, of ion, is smaller than the dielectric constant of water. And this is, in general, for small concentration. For simple ion, it's a general statement. Of course, if you have some complex ions or you go to high concentration, things can change. But in general, this is a general statement, although I just presented it with some hand waving. Now, if you look on experiments, and I have to show this figure because you see this, it's a very old experiment. You can see how they drew it by hand, not like today. But basically, this is a result that is true even today. And look at the numbers. The dielectric constant of water with no salt, N is the constant density of salt, so it's 80. And then if you go to, let's say, 2 molar, which is quite a lot, it goes to 60. So it's a substantial effect. For seawater, which is like 0.6, it will be like maybe 70 or 70 something. So it's a substantial effect of the decrease in dielectric constant. Of course, you do this static dielectric constant by, you don't want to introduce flow of ions in the solution, so you do it at frequency, at high frequency, kilovolt, hundreds of kilovolt, and then you extrapolate to static, to 0 frequency. So the initial decrement is linear. So like you can see here, I called gamma the constant, the prefactor of this linear relation. And you see that it's in units of 1/mol, molar, it goes like between 5 and 15 for simple ions. And this is well known, well tabulated. I'm not sure what is this salt, maybe NaCl, but many salts show the same thing. So together with Henry, of something more than in 2007, we thought of how we can incorporate in a simple system also the granularity of the water, the fact that water is created from molecules that have a permanent dipole that can rotate. And so we had a augmentation, we had a change in the Poisson-Boltzmann where we took into account also the dipoles of the water. And so you see we have ions at concentration n0 and dipoles of permanent dipole of the water that can rotate of some other concentration nd. So this is what we call the dipolar Poisson-Boltzmann. The free energy, I'm showing it first, only the first two terms that has to do with the ion. This is the regular one, E squared, and this is come from the entropy of the ions. And these two terms, if you take variation, you will get the regular Poisson-Boltzmann equation, only for ions. But if you have also dipoles, it becomes more complex, and this is how it looks. So you have one other term that has to do with the dipolar density in the free energy, and variation of this term give you this type of term. You see it's quite complex, non-linear, but numerically is no big deal to solve. E is, of course, minus the gradient of psi, and you see that it's very important to note that charges, monopole interact with the potential, while dipole interact with the derivative of the potential, which is the electric field. This is the way that it goes. So the other thing that is important to note is that it's additive. You see, there is no interaction between the density of ions and the induced density of charges that come from the dipole. And this is because this is mean field level. So on mean field, there is no interaction. And you will see that in order to calculate the dielectric decrement, I need to do more. But what I can do, even on this level, is to solve, just as I showed you before, one ion that I put in water, and I calculate the profile of the dipoles. And by calculating the profile of the dipole, I can calculate the dielectric change locally around the central ion by solving point ions embedded in dipole in my dipolar Poisson-Boltzmann equation. So it's like a boundary condition. Let's say at the origin I have a point charge, and then I have my dipole, and they will react to this point charge. And the way that they react, you can see here, this is a distance from the ion, the radial distance. And you see it starts from 0, and then it goes to 80. So close to the ion, the dipoles are much more localized, as I explained before, and our theory produced that. And there is actually a characteristic length, which we call the hydration layer thickness. And in our theory, it depends very simply on the strength of the dipole of the water molecule, and the Bjorn, the 7 angstrom that I introduced before. Now, if you want to do more, you want to calculate the decrement, you need to take into account the fact that you have a soup of ions and dipole together. and you also have some coupling of the fluctuation of 1 degree of freedom versus the other, because this is a dielectric constant. You want to see what is the response of the solution as I am changing the number of ions. And in order to do that, I'm not showing you here the details, but together with Henri and my students, we were able to devise a field theoretical approach where we can go to the first correction to mean field. We go to the first order, what is called the one-loop correction. And in this one-loop correction, there are couplings between the fluctuation of the dipole densities and the ionic densities. And what I show here, we have a whole formula that takes also into account the fact that the ions and dipoles have finite sizes, which I call A. Here, the finite size of the ion. I'm not showing you the whole formula, it's just a complex formula. It's a long formula, but I show you an expansion that is possible to do for low salt concentration. So it's power of n. You see, it's not analytical power of n, it's n to the 3/2, but remember that the Debye length itself is related to n to the minus 1/2. So it's more or less the expansion in powers of the Debye screening length. And what we get, you see, we get the decrement. This is for low concentration. But then we have a correction with an opposite sign, with a positive sign, which goes to n to the 3/2. And this coefficient comes in, we can calculate directly from the theory, and they depend on various parameters like the size of the molecule, the Bjorn length, and so on. And in terms of fitting, the fitting is excellent. So we have the size of the molecule that we fit, and we can fit in such a way also the beginning, the linear decrement, but then the deviation from linearity. And you can see these are different salts, and the fit is quite good. And then different temperature, and again, the fit is quite good. And all of this is done by this one-loop correction to the mean field. In the mean field, you don't have any result of this sort. Okay, so this was the first topic. And the second topic is directly related to a very beautiful work that Onsager did with a colleague of him, Samaras, in the 30s. And what I recommend, if you are interested, don't read his paper. He was extremely mathematical oriented. Maybe many of you here are also, but read the way that Landau and Lifshitz explain it in their statistical mechanics book, because it's really very, very nicely done. Maybe not all the coefficients are calculated to the last detail, but all the essential physics is in the Landau and Lifshitz. And we also improved on that, and you will see in a second how we improved on that. So let me tell you without the detail what was the idea of Onsager and Samaras about. So the dielectric constant of bulk electrolyte goes down because of this effect that I told you, that you have the hydration shell, and then, of course, when the ions are concentrated, you have correlation of the ions and the dipole. For surface tension, another well-known fact, which is experimentally known, it's not such a big effect, but it is an effect that can be easily measured. Surface tension of seawater is higher than the surface tension of pure water. I mean, one way of looking at it is if you bubble, let's say, nitrogen or air through a column of pure water, and then you put a lot of salt, and you bubble, you form bubbles that, of course, are transient. The bubble will break. But you can see how the bubble in seawater break faster because the surface tension is higher. So what was the idea of Onsager? The idea was the following. You have your water with the salt. And we are not interested now. It's very nice and important problem. Why is the surface tension of water so high and so on because of the structure of water close to the interface? We are just interested on what is the extra effect of ion that I put in the electrolyte that I put in the water, how they will increase the surface tension. This is all. So everything is with relative to pure water and surface tension of pure water air. So I have an interface of water with air. There are no charges on this interface to start with. But what there is a strong dielectric discontinuity, yes, because you go from epsilon of water, 80, neutral boundary, you go to 80. So you have a jump in the dielectric constant. And of course, we know that one of the ways to model such a jump in such a simple geometry is to use image charges. It's very convenient to do in 2 dimensions. So I can forget about the boundary, and instead of that, I can say that each ion has an image charge, and together with the image charge, they will solve the boundary condition, the discontinuity of the dielectric constant, or the discontinuity of the vertical electric component. Now, the ions is inside the dielectric media, the water, with the high dielectric constant. If you look on this little calculation, you see that the ion, the image one, will not have an opposite sign. It will have the same sign as the real one. So you have 2 ions, both, in this case, both are negative, so they will repel each other. Now, if ions repel each other, this means that the ion that is in the water doesn't like to be close to the water. The more physical reason is that when it comes close to the water, you disrupt the hydration shell around it. And it likes to be inside the water where the hydration shell is complete. But in this way, you can see it via these image charges. So ions are depleted from the interface. The density close to the interface is lower than the density inside the bulk. Now, when you have a depletion, it means that the surface tension is increasing. In soapy water, the reason that surface tension of a soap solution is lower is because the soap likes the interface. It has a part in the molecule that doesn't like the water. It likes to be on the other side, and it reduces it's a adsorption problem, and then the surface tension is reduced. Here, for simple ions, the surface tension is increased because of the depletion of the ions. Okay, so this was one ion. It's only one part of, so there is this interaction of the ion with the interface due to the image charges. And this is one thing that Onsager did. The other thing is, of course, you have to take into account all the other ions around. There is not only one ion. And if you do it, you use the Debye-Haeckel theory for electrolyte. Again, you can read about it in Landau and Lifshitz or other books. And together with this dielectric continuity and the presence of all the other ions that are screening the interaction, Onsager found that the increase in the surface tension in units of kT goes as n log n, where n is the density of the bulk of the electrolyte. So it's very elegant, simple result. It's ion. It's not specific to any ion. It's just specific to the fact that you have some concentration of ion in your solution. That's all. And maybe to the valency of the ion that come through the Debye length. So the surface tension increased with salt, and it's not specific. Okay, so you have to go back to experiment. You cannot just leave it like that. And these are experiments, rather recent one, 20 years ago. And you can see that, so this is a curve of the increase of the surface tension. Yes, I'm plotting here the delta gamma, the increase of surface tension in units of millinewton per meter standard versus the density of the salt in molar. And you can see that the Onsager result is deviating a lot from this homologous series of fluorine, chlorine, bromine, iodine. And actually, it's not very nice. It's only here at very low dense salinity of 10 millimolars, which is really low, 1/10 of physiological condition molarity, that the theory works. So this means two things. First of all, that the theory of Onsager Samaras, which has very beautiful ingredients, can work only at low concentration. But the other thing is that it cannot model the ionic specificity that you see from experiment. You see this open up of the result, and it's quite substantial. The increase is not so much. It's a few percent of the total surface tension, but you see that the fluorine, chlorine, bromine, and iodine, they really open in a very particular way. Always the fluorine will be on top. Then if you look in the periodic table, the fluorine is the first, and chlorine, bromine, and iodine, in terms of the atomic mass. So what is the reason for that? Yes? But if you can raise up your voice, because I don't hear so well.
Where the scale in the log of n, what is the scale for log of n?
The scale was k. I didn't write down the prefactor, but you will see it later. Okay, it's kt, but some prefactor, and has to do, for example, epsilon of water minus epsilon of air divided by the sum. You will see it later. I have a formula. But this is with the right scale. It's not that I plotted it with the right scale, and it matches at very small densities. Okay, so this phenomena that you have ion specificities that always go in the same way between ions. You see, these are all, you look in the periodic table, they are all in the same column of the periodic table. It's very simple. Fluorine, chlorine, bromine is always, you have one electron above the closed shell. And we can also have the same thing for the positive ones, the alkaline one, where you have one electron below. You're missing one electron to close the shell. And this was known even at the days of Onsager and Debye, because a German pharmacologist named Hofmeister worked on this phenomena in the late 19th century. So this is not restricted only to surface tension. In many systems, he works on coagulation of egg protein, of egg albumin, when you in presence of some salt. I mean, you know that if you take a raw egg and you put it in salty water, you don't need to heat up the egg to make it hard. Just the salt or some acid, vinegar will solidify because it will denature the protein. And this is something that is studied systematically. And the series is here. You see, this is a series. This is more stabilizing and less stabilizing. And fluorine, chlorine, bromine, iodine is exactly the way that you have in the series. And you have dozens of different experiments where this ion specificity is entering. So this is the real effect. It's, of course, not in this simple idea of Onsager, because it just took a point dipole and a point ion, and that's all. It didn't take any specificity of the ion. OK, so of course, we were not the first to look at this system. There were many other. I'm not going to tell you the history of the system, many numerical liquid theory simulation, and they found similar effect that we did. What we did, and this is together with Rudy Podgornik, a good friend of mine, and my student at the time, Tomer Markovic. So what we did is we used field theory, and we looked at the same problem where we introduced one phenomenological parameter, which we call alpha. And alpha is characterizing the adhesivity, the different adhesivity of different ions. It's a fitting parameter. You can calculate it also from first principle. We didn't. And in our theory, we were able to reproduce, first of all, Onsager result. We have the full Onsager term, and Bernard, you're going to see that. But there is a correction which depends on the specificity, namely via this alpha. And we also do this one loop expansion. And this is the result. So Bernard, this is the exact term of Onsager. Of course, it's a bit delicate what you use as a cutoff as A, but you need to do a cutoff because the Coulombic interaction will diverge at 0 distance. You need to put a cutoff. And then we have this correction term. You see it's ion specific because of this alpha. And I express it in terms of effective surface charge, sigma E, which depend on this alpha. And with this extra term that we were able to obtain on top of the Onsager Samaras, and by the way, also the Onsager is something that not many people appreciate. The Onsager Samaras theory by itself is not mean field. Because once you take one ion and you put it in solution, you already broke the mean field. Because mean field would mean you put a whole layer, and then you will get nothing. So Onsager Samaras, in their way, they did something that goes beyond mean field, but they didn't take into account this ion specificity. And if you do the curve that I was showing before, these are our fit curves with these alpha parameters that vary depending on the type of ion. It's a fraction of kT, which is quite reasonable. And we were able to really have nice fits in this system where, because the interface is neutral, so you don't have to start with any surface charge distribution, the effect of fluctuation is very large, because usually the fluctuation goes on top of some average, and here the average is 0 because you don't have any surface charge to start with. It's only the fluctuation of the ion density close to the interface. Okay, so the third thing that I'm going to talk about, and maybe it will take me 10 minutes, is very recent work that was published this year together with Henri and with my students. And this has to do with conductivity of concentrated ionic solution. It's for the purpose of this talk, this is the wrong thing that Onsager came and told Debye that his theory is wrong. So on this topic, on the topic of conductivity. And actually, it's, if you read this in the collected work of Onsager and this nice introduction, biographical introduction of Michael Fisher and others, you will see that this was the first time that Onsager thought about the reciprocal relation, because what was wrong with Debye and Haeckel was that they didn't follow this reciprocity between an ion that moves with all the cloud of other ions. They took the ion that moves holistically and all the other cloud is diffusing. But you cannot do it like this. You need to close the circle. You need to, because each ion has the cloud of the other ones. And this was what's wrong, and this is what Onsager corrected. And of course, Debye agreed with that. And then the theory is called Debye, Haeckel, Onsager nowadays. You will see. OK, so let me start with conductivity. Of course, conductivity of any system. You put some electric field. You put a, 2 electrodes of a battery, and you measure the current. Now, so the conductivity, the constant, is just the ratio between the current. Let's say you have a steady state system, the average J, divided by the external field. In an electrolyte, you have 2 carriers of charges. You have the cation and anion. It's like in a semiconductor, you have holes and electrons. And so if you put the system, water with some salt under a battery, you have 2 currents. In my cartoon here, the anion flow to the left and the cation flow to the right. So you have to add up the currents, yes, because both contribute both species contribute. And in order to find this conductivity, you take a small field and you set it to 0. So this proportionality between J and E, the conductivity constant coefficient is not, it doesn't depend on external field. Of course, you can do conductivity in presence of a strong electric field, and this is something else that I'm not going to talk about. OK, so what was known even before 100 years ago is something very simple, that in the dilute limit where each ion is moving and it doesn't see any of the other ion, you just add up. You add up all the ion that goes to the left with all the ion that goes to the right. The cation and anion, let's say they have different mobility. So kappa 0 is this, the dilute limit is proportional to the number of ions that don't see each other, times this constant that is coming from the average mobility. And this is why you have the factor 2 here, because the average I'm dividing by 2. So altogether, I'm just summing up the two currents. OK, so this is well known for very, very dilute system where the ion flow and they don't see each other. But by Haeckel, and then with the correction of Onsager, they did more. They looked at dilute system, but where the ions do interact. And so you can see here, this is the exact analytical form. I put it in terms of another length. The RS is just the Stokes radius, yeah? And you see that it depends on the viscosity. Yeah? If you have let's say a sphere that moves in a viscous fluid, so you have this, you have the viscosity, you have the mobility, of course, and this is the RS. And you see that the kappa D is reduced. You see the minus sign here and the minus sign there. So kappa D is, kappa with the salt is reduced with respect to this infinitely diluted kappa 0. And the reason, there are two reasons for that. One is a direct interaction between the ions. Imagine a negative ion is flowing from my left to my right, and the other one flow from my right to my left. But when they are close together, they start to interact because they are attracting each other. So they will spend more time together. If they spend more time together till they pinch off, this means that the effective conductivity will go down. And the reason for that, there is two reasons. This is a hydrodynamically mediated electrostatic interaction. It comes from the backflow of the fluid. And the other one is a direct interaction. And you see that here, the viscosity of the fluid enters. And in this direct interaction, of course, it doesn't enter. So this is the cartoon, that you have two ions that come together, spend more time together, because the concentration is such that this event starts to be more important. And then they pinch off, but during the time that they are together, it will reduce the conductivity overall. OK, so this is the Onsager. See, it's very elegant, Onsager Samaras Debye. And what does real experiment tell us? So this is what real experiment tell us. I take, again, very simple salt, but there are many other. And you see, for very low concentration, this is in molar, so it's up to 10 millimolar, 0.01 molar. You see that their theory works very nice. So you get this reduction because of the reason I explained. You get the reduction in conductivity, and it works nicely. But if you start to go to higher concentration, there is a problem. This argument that the ions spend a lot of time together is too strong. And you see that the theory goes very strongly. It even goes below 0. So after about 10 millimolar, the theory doesn't work. It's really deviating a lot. And this is usually the case that when it's very dilute, you can ignore fluctuation, you can ignore many things. But then you see that this is experiment and theory doesn't work. So something is missing. And again, I'm not claiming that what we did was the first time that people looked at it. Many people looked at it with liquid theory, with simulation. I'm not going to account for them, but I'm just going to tell you a little bit about the theory that we did together with Henri and my student. And the theory has to do with the fact that in the Onsager theory, the ions were point-like. So if they were point-like, they could come very close to one another. And because of the strong attraction, 1/r, they would spend a lot of time together till they pinch off. And this is an overestimation of this effect. So what we did was we tried to take into account the finite size of the ion. The fact that if the ions have a finite size, they approach each other, but they will not really overlap. They will approach each other up to their size. And this effect really is substantial and can correct the theory of Onsager and Debye in a very nice way, and the fit to experiment is excellent, as you will see. So the theory is based, I'm not going to tell you about the detail, but it's a stochastic density functional theory. It's based on work of Kawasaki and Dean from about 20-something, 30 years ago. And then Dean, Dean works, is an Englishman, but works in Bordeaux. David Dean is quite a prominent physicist. And the theory had, the current had these 4 different sources: advection, because of the fluid is moving; diffusion, of course; the electrostatic force, that this type of interaction between charges; and the stochastic current that goes in this way. And our modification was in terms of the electrostatic interaction. We couldn't really take into account the real hard core of the interaction. It's usually very hard to do in analytical field theory. So we took some modified softer potential, where basically instead of having a diverging electrostatic interaction when the 2 ions come together and are attracting each other, we have a saturation at some point. So in some sense, it's like partial overlap, but we checked this, and the results are very good. And I just want to show you. So again, you can have to this first order correction, the loop expansion, you have a whole analytical form. It's up to some complicated integral. I'm not going to show that. But what I'm going to show is a simple expansion in powers of A, the size of the ion, divided by the screening length. And you can see here very nicely how we correct the theory of Debye and Onsager with this exponentially factor that depend on A over lambda D. So just that you will remember, so this is the original theory. So it's a very simple, at least in this low A over lambda D or low concentration, medium concentration, let's say, limit, we can get this very simple correction, which has to do with the exponential factor of A over lambda D. And with no fit parameter, you take A from the literature, you take it as the crystallographic size of the ion, we get excellent result. With no fit, there is no fit parameter in the theory. You see the theory works up to 3 molar, which was very, very surprising. Of course, if I will go to 6 molar close to saturation, the theory will fail, because it's not an exact theory. But in a large window, and 3 molar is a lot. 3 molar is half the saturation of salt. It's half the concentration of the Dead Sea in my country. So, so you see, this is the 2 different type of approximation. This is the Onsager theory. We didn't do it only for 1 salt. We did it for many salts. We also did it we fit a different temperature, and the fits are very nice. So this is the end of my story. I want to just to conclude by saying that I related to works of the great Onsager in 3 different ways. I started by explaining you how hydration shell and this fluctuation effects can cause this dielectric decrement of salty water, of brine, of electrolytes in water. Then I went and explained you how ionic specific effects can change the surface tension of electrolytes for different type of electrolyte. And finally, due to the finite size of the ion, we can correct in quite an elegant way. We can find a model that fits very nicely conductivity of simple ions. Of course, as I told you before, conductivity is measured in this in this extrapolating limit of small electric field, and then you take the field to 0, and this is like the conductivity of 0 in this limit of 0 electric field. Before I conclude, I would like to acknowledge my collaborators. So these are or actually were my students. Ramadar is now a postdoc with Jean-François Joanny at Collège de France. Yael Avni is working now as a postdoc in Chicago with Vitelli, with Vincenzo Vitelli. And Tomer Markovic worked with Fred McIntosh at Rice, and is now on the faculty of our university and the engineering school. And of course, I don't have to introduce again Henri, with whom I have enjoyed a lot of collaboration. But the other person with whom I worked a lot is Rudy Podgornik from Ljubljana, but in recent years he's working in Beijing. I'll finish here. Thank you very much for your attention, and if you have any questions. Yes.
The first name of Bertrand Duplantier is Bertrand, not Bernard. Okay.
Because of the COVID, I forgot everything.
Okay.
But nevertheless, his article, he has an article which he showed me, like maybe it was 2015, 100 years after Annus Mirabilis. And your article on the Brownian motion is beautiful, and I learned many things from there. So I want to acknowledge this.
Okay, so this is a good excuse for
Forgetting
the name. Any question? The talk was very clear, so I don't know if... yes, Michel.
But can you just speak up, because I have some problem here.
If this can be done at the level of a colloquium, can you say a few things about the field theory you use for your work? Because you mentioned several times the use of field theory,
Yes.
but you never
That's right.
described it. So is it doable on the
Just
spot?
to explain it, so okay, I mean, this is a great master of working on field theory of various systems, and so you start with point-like charges, and you transform it into continuum degrees of freedom of potential and things like that, and you have some, you have like a partition function, and then you formulate it in this way, using usually Hubbard-Satonovich, what Henri likes to do, transformation. And on that, you look at the saddle point, and then you make correction with if there is a small parameter. And this basic, it's in the bulk, it's easier. Close to the surface, it's more complex, because you need to take into account the surface. But so there are different way of doing it, but it's essentially the same thing and trying to account for fluctuation which go beyond the mean field.
So just to maybe as a precision, the standard field theory for electrolytes, for salt, is sine-Gordon in dimension 3. No, sine. Yes, sinh is when you go to imaginary, because you have to go to imaginary field.
Sine, sinh, but the field theory is sine.
Yes.
Yeah, and actually I also want to say that the great Sam Edwards was, in the late 50s, he was one of, I'm correct in that? Yes. He was one of the first to, because he was a student of Schwinger, so he knew many of so he was one of the first to formulate the field theory of Coulombic system, among the zillions of other things that he did, and it was,
Yeah, in your correction to the surface tension of electrolytes, maybe I'm wrong, but I have the feeling that you are using only one length for a salt, but in fact you have anions and cations, and we know that if you change the cations, you focus on the anions, but if you change the cations, you will get different results.
Yeah.
So could you elaborate a little bit on this,
so
and justify the assumption?
it's an excellent question. I don't say it just for politeness, but it's really a question that I was sort of hiding under the rug this, because what happened is that, you know, the anion, you know, so I showed an homologous series. I think it was always sodium with fluorine, iodine, or something like that. And if you look on the profiles, also from simulation, the two types of ions, the positive and negative, are very different at the interface. And the fact that one is more attracted than the other, you create a local charge density difference. And this actually is what is causing the effect. So it's very important, the fact that not only the different anions have different alpha adhesivity, but also you have a gap, you have a difference between the cation and the anion. We did take this into account with our alpha and in some approximate way, and so this is a real effect. Also in simulation you see it, Roland nets, for example, but this is a very good point. I mean, and you really need to be very careful about the cation and anion. They don't behave the same at the interface, and one of the simple way to see it is, if you look on point dipoles, of course there is no difference if the arrow is pointing towards the ions or like this. But if you have a water molecule, it's very different if the two hydrogen are pointing towards the ion or if the oxygen is pointing, because the molecule is not symmetric. And this is one of the reasons that the hydration shell is different for cation and anion.
Even if you take, for example, HCl, depending on the concentration, you might have an increase or decrease in surface tension, depending on the concentration because of screening.
Maybe you can repeat, maybe,
yes.
Also for the Zoom.
If you take HCl, hydrochloric acid, because of the dissymmetry of H and Cl inside, you may have increase or decrease in the surface tension, right?
Yeah,
because
absolutely.
Yeah.
So, especially for acid, I think also for phosphoric acid, when you have very small concentration, it usually goes down. But there are cases where it's either start flat or even start up. But even when it goes down, sometimes, I mean opposite. Yeah, it goes up and then it goes down, because when it's a more complex constitute, you have also the polarizability of the molecule itself. You have partial charges on the more, and this is so this, what I'm saying is, for this simple, the most simple salt, the alkaline with the halides, so this works. But also if you look on the high atomic number, you can find that sometimes it's even going a little bit on the opposite direction.
Okay, maybe last question.
So just in the last part of your talk, you had you want to take into account the volume, right? And so even though you take a soft potential, in liquid theory, it's hard to close the hierarchy. So how do you manage that? Maybe in a word.
Because
maybe you repeat for the Zoom.
It's okay.
Repeat for the. It's okay.
I have them.
Okay. For me.
Because of the soft core potential in the last part.
The last part, yes.
Because of the soft core potential, you don't take into account correctly correlations and things like that.
That's right. So you are absolutely right, and our result works very nicely up to, let's say, 3 molar for monovalent ion and maybe half a molar for divalent ion. But if you look after, you deviate. So after means that the ions become much more concentrated, and then this approximation is not anymore good. So the surprise, we knew that it will be better than Onsager Debye, but we were surprised that it really went all the way to 3 molar, and 3 molar, if you calculate in terms of the distance between ions, is already a very small distance. So it works very nicely, and then it deviates.
So you basically use maybe Dean's equation, and you do some kind of loop expansion on that equation, if I understand.
It says we use Dean's equation and then do some kind of loop extension on Dean's equation.
Is it?
It's
Yeah.
the same
Okay.
Yes,
It's the same.
yes,
Okay.
yes.
Alright.
It's the same idea, but he in his work with Demery,
Mhm.
he used point
Okay.
charges, and we didn't.
But in Dean's equation or in this kind of
Yeah, and also
equation,
they
we-
don't have the advection, I think. or
Yeah,
something.
they don't have the advection,
but in principle, it's the same approach, but maybe we took into account more effects. But in principle, we are following him. I think he didn't have the advection, if I'm not mistaken.
Okay. Thank
You
you.
know, the backflow of the fluid. You wanted to ask something?
Thanks. You mentioned at the beginning the DNA and all the membranes and the cells, and I know that some membranes leave. I mean, some ions can go through, some ions cannot, and I wonder if you could say something about conductivity in these cases, where only some ions can go and not all. And
You mean the permeation of ion
I-
through the membrane?
yeah.
Okay. So, so I want to say two things, but this is not related to my. It was just motivation. There's a lot of other works on that, but I will tell you a few things that I know. The first thing that is very important in biological membrane is that there is an asymmetry between the outer leaflet and the inner leaflet in terms of the distribution of the charged lipid. It's an active process with a flip-flop where there is more charges on the outer layer than in the inner one. Of course, when the cell dies, after some time, hours, it will equilibrate. But the cell itself, in an active way, is producing this. This is one interesting and important thing about a living cell, that it's not the same. The other question that you ask about the permeation, so most of the permeation of ion is done through channels, ionic channels, which are special protein, which have a protein which has a hole inside, or pumps. But even the ion channels are specific, so it will be easier, let's say, for a potassium to go in than for a sodium. And this is the main reason that ions don't permeate in the same way that potassium and so. For example, for neuron conduction, it's very important to have this gap between sodium and potassium. But it's not done. Okay. Of course, ion can also permeate through the membrane itself, but this is a much slower and much smaller effect. Most of the ion are permeating through these channels and pumps.
Okay, last question by Hubert.
Isn't there some sort of large n limit where you can do calculations? After all, if you have only ions and a few molecules of water, it should be similar to small n. I was expecting some sort of n goes to 1 over n duality.
I didn't understand the large. What is large? N?
N, your density. Isn't there a large n limit where you can do calculations? After all, if n goes to infinity, you're having only ions and a few molecules of water. Therefore, this should be the same as n small. I was expecting a duality. N goes to 1 over n.
Okay. But we have a finite system. So you are talking about increasing the density of ion versus
Absolutely.
water.
Yes,
Yeah.
yes.
Okay. So I can tell you two things about that. First of all, is that of course you always, if you go above 6 molar, like in the Dead Sea, you will create back the salt. So the liquid cannot be saturated all the way.
Okay,
But I have also another comment. If you don't look at simple liquids, at simple ion, but you look at more complex ion, and this is done a lot in fuel cells and batteries and other applications, then you have what people call ionic liquids, where there is no solvent, just at room temperature, a liquid, not molten salt at 1000 degrees like sodium, but at room temperature, because of special consideration of the asymmetry of the charges of the negative and positive ion, you have an ionic liquid where there is no water, but this system by itself is also, it's not so, it's a system that has lots of, the importance of correlation there is very important, and it's not so easy to solve this system. This is my point.
You cannot solve it exactly.
Yeah. Because it's not an easy starting point. So